On the topic of power series, we're usually interested in finding the solution for a differential equation using power series. This differential equation is given to you as y prime minus y equal to 0, or dy over dx, the rate of change of y with respect to x, minus y is equal to 0. What is a general definition of a power series? A power series around the center 0 is defined as the summation of an x to the n and start from 0 goes to infinity. This is the general form of the solution. Y equals to the summation of an x to the n. Now, we need to find the derivative of this power series and plug that in. Let me move this a little bit. I'm going to write this guy in expanded form and show you when you're taking the derivative what happens. If you write this guy in expanded form, y can be written as a sub 0 plus a sub 1x plus a sub 2x squared plus the rest of the terms. So if you want to take the derivative of this, it means that you're taking the derivative term by term. The derivative of constant is 0. The derivative of ax is a1. The derivative of a2x squared is 2a2x plus the rest of the terms. But what is the pattern that you're seeing here? You're basically taking the derivative of x to the n. So y prime can be written as the summation of an times n x to power n minus 1, but now your n starts at 1, goes to 0, goes to infinity. So if you plug in 1, you get a sub 1 times 1 x to power 0, which is the very first term that you see here. If you plug in, this is n equals to 1. If you plug in 2, you get a sub 2 times 2 x to power 1 plus the rest of the terms. This guy is exactly the same as this term here. So please note that you have to shift the index of your power series to 1 instead of using 0. That's one of the most important keys when you're finding the solution of differential equation using power series. Now let us substitute y equals to the summation of an x to the n and start from 0 to infinity, and y prime, which is equal to the summation of an n x to power n minus 1 and start from 1 goes to infinity into the differential equation y prime minus y equal to 0. Our goal is to find a relation for these coefficients. A relation between the coefficients. So let us begin. Y prime minus y is equal to 0. It means that the summation of an times n x to power n minus 1 and starts from 1 goes to infinity minus the summation of an x to power n and starts from 1 goes to infinity is equal to 0. In order to combine these two series together, we need to shift this. So this is 0, nothing. We need to shift the index and introduce some dummy variables. Please note that you cannot combine these two series with different exponents here, since we have different powers, n minus 1 and n. We cannot combine these series yet. What are we going to do? We're going to just shift this a little bit, right? In order to shift this, I'm going to introduce a dummy variable. Let k be equals to n minus 1. So n becomes k plus 1. Wherever you see n, you're going to use k plus 1 in the first series. Okay, your first series becomes the summation of a sub k plus 1 times n, which is now k plus 1, x to power k. Okay, since n starts at 1, your k starts at 0. K starts at 0 and then goes to infinity. Make necessary adjustment to this series, minus the second series, which is negative summation of an x to power n, and then right hand side it is equal to 0. Okay, please note that here you're using a different letter, k and n. Now you can switch this guy, relabel this to n. Let us relabel k to n. So wherever you see k, just write down n. Your first series becomes the summation of a sub n plus 1 times n plus 1 x to power n, as easy as that. And now n starts from 0, goes to infinity. Very well. What about the second series? The second series is minus the summation of an x to the n starts from 0 to infinity. On the right hand side you have 0. But note that since you have the same exponent, you have the same starting index, you can combine these together. So now we can combine these series. You're going to write down the first, just one of these sum, and then an plus 1, I'm not going to use different colors now, times n plus 1, x to power n, minus an, x to power n. On the right hand side you have a 0, and starts from 0, goes to infinity. You can factor out x to the n. So you can find a recursion here. You have the summation of an plus 1, n plus 1, minus an, x to power n. On the right hand side it must be equal to 0, but this series is 0 if and only if this quantity is 0. This series is 0 if and only if an plus 1 times n plus 1 minus an is equal to 0. That's how we can find a recursive relation here. Let us set an plus 1, n plus 1 minus an equal to 0. We have the following formula. An plus 1 times n plus 1 is equal to an. So an plus 1 can be written as an divided by n plus 1. This helps us to find a sub 1, a sub 2, a sub 3, and so on. This formula helps us to find the coefficients. So, for example, when n is equal to 0, if n is equal to 0, what do you have? A sub 1 becomes a sub 0 divided by 1. When n is equal to 1, what do you get? A sub 2 is equal to a sub 1 divided by 1 plus 1, or a sub 1 divided by 2. When n is equal to 2, a sub 3 is equal to a sub 2 divided by 2 plus 1, or a sub 2 divided by 3. But I have a relation for a sub 2. I know a sub 2 is a1 divided by 2. So I'm going to substitute this guy here. A sub 3 is a sub 2, which is a1 divided by 2 over 3, which can be written as a1 divided by 6. a1 divided by 2 times 3. Very good. Excellent. Let's see. What if n is equal to 3? When n is equal to 3, a sub 4 becomes a sub 3 divided by 3 plus 1, or a sub 3 divided by 4. But take a look. I already know what a sub 3 is. A sub 3 needs to be replaced here. This is my a sub 3, right? So this guy can be written as a sub 1 divided by 2 times 3 over 4, or you end up with a sub 1 over 2 times 3 times 4. Ooh, I see nice pattern here. 2 times 3 times 4. We can continue this process, all right? In general, if you continue this pattern, we see that a sub n plus 1 or a sub n can be written as a sub 0 divided by n factorial. So let's go back to our series. Take a look. Here is the series that you had with the general term. You wanted to set this guy equal to 0. You found a pattern, right? The pattern is a sub n is equal to a sub 0 divided by n factorial. So what's the meaning of that for our power series? Okay, let me just erase this one. Your y is equal to the summation of an x to the n. So y can be written as the summation of a sub 0 divided by n factorial x to power n. N starts from 0, goes to infinity. Or basically, what your y is equal to a sub 0, whatever that number is, times the summation of x to the n divided by n factorial. But I know this pattern. I saw this pattern before. Recall that e to the x is equal to 1 plus x squared divided by 2 factorial plus the rest of the terms, or it was the summation of x to the n divided by n factorial and starts from 0, goes to infinity, right? So if you plug in 0, you get a sub 0 times the plus the rest of the terms. So your y is equal to a sub 0 times e to the x. This guy is exponential function e to the x. So that's how we solve this differential equation, and this is the solution for this differential equation in power series form. You can also write y equals to a sub 0, the summation of x to the n, divided by n factorial and starts from 0, goes to infinity, or a sub 0 e to the x. The solution of the differential equation, y prime minus y equal to 0 is a sub 0 e to the x. Now let us recap what we did here. We wanted to find the solution of this differential equation using power series that we learned in this class. So for the power series, a power series in general is defined as the summation of an x to the n and start from 0 goes to infinity. We take the derivative of that as well. Why? Because we need to substitute these into the differential equation and find the recursion formula to identify these coefficients. Y prime minus y is equal to 0, and our goal is to find a relationship between the coefficients. What we did, we introduced some dummy variables, we relabeled these, and we saw that this can be written as the summation of an plus 1, n plus 1, x to the n, minus the summation of an, x to the n, and start from 0, goes to infinity. When you combine these together, this is the recursion that you get an plus 1 times n plus 1 minus an is equal to 0. So an plus 1 is equal to an divided by n plus 1. You can also see it this way as well. An is equal to an minus 1 divided by n. If it makes it easier for you to recognize the pattern this way, these are equivalent to each other. You can switch this with any variable that you like. When n is equal to 0, it's easier to recognize it this way. When n is equal to 0, a sub 1 is equal to a sub 0 divided by 1. When n is equal to 1, you get a2 in terms of a1, which can be written as a sub 0 divided by 2. So wherever you see a sub 2, you can use a sub 0 as well. So you get a sub 0 divided by 2 times 3. Here you get a sub 0 divided by 2 times 3 times 4. So in general, the pattern that we see is we have an equals to a sub 0 divided by n factorial. But if you write this guy, it means that the solution is in the form of a sub 0 x to the n divided by n factorial. But recall that from Maclaurin series, e to the x was the summation of x to the n factorial. So you have a sub 0 times e to the x as the solution of this differential equation.